Good morning and welcome to TME Presents, a hybrid solution to generator efficiency. You've read the article, now learn the rest of the story. I'm Daniel Wheatley, Associate Editor for the Military Engineer, and it's my pleasure to welcome you here today. Before we get started though, I'd like to go over a few items so you know how to participate in today's event. All the attendees are in a listen-only mode for the presentation. You can submit questions for the presenters at any time by using the questions pane of your control panel. We will collect these and address as many as we can during the Q&A session at the end of the presentation. Please also submit any technical issues you may be encountering here as well. Originally published in our May-June 2020 issue, A Hybrid Solution to Generator Efficiency covered work by the U.S. Army Engineer Research and Development Center's Construction Engineering Research Laboratory on developing a hybrid system for operational energy. While many installation energy needs are currently solved with oversized generators, research has led to the development of a hybrid system that can deliver considerable fuel economy. After a deployable metering and monitoring system study found that most tactical generators in contingency environments are typically loaded to only 30% of their rated capacity, the U.S. Army Engineer Research and Development Center's Construction Engineering Research Laboratory saw an opportunity to deliver a solution. The resulting technology, the hybrid power system, works with program of record, legacy, and commercial generators to optimize energy consumption efficiency. I would now like to introduce retired U.S. Army Captain Tom Decker, Operational Energy Program Manager, and John Goebel, Operational Energy Technical Manager of the U.S. Army Corps of Engineers, the Engineer Research Development Center, Construction Engineering Research Laboratory, the authors of the article. Tom and John, you now have the digital floor, so take it away.
Thank you, Daniel, for the introduction. I want to thank everyone for being here to listen to the presentation. You can go ahead and go to our slides, Daniel, if you want. So we'll be talking about, like Daniel said, our hybrid power systems. Next slide. So first I wanted to kind of start with why did we start down this path to begin with? Well, when we were looking at statistics from Iraq and Afghanistan, we saw that 52% of all casualties happened during resupply missions. As you can see, half of all of these resupply missions were from delivering fuel. We knew that if we became more efficient with our resources, we could save lives downrange. This was, and this is, the driving factor for the research that we conduct. Next slide. Learning this led to the development of an operational energy team within our lab. We structured this team using a cyclical model, as you can see here. We realized that power and energy demands fluctuated based on numerous variables, and every aspect of operational energy supported each other. Next slide. Through this, we also developed 2 test sites to support not only operational energy, but other operational research within the Department of Defense. ERDC-Forward Operating Base Lab, or EFOB-L, is located at our lab in Champaign, Illinois, and it gives researchers the opportunity to test projects with program of record equipment, such as generators, structures, power distribution. We also own a training area on Fort Leonard Wood, Missouri, called the Contingency Basing Integration Training and Evaluation Center, or CBTEC. This is a larger test site, and soldiers regularly use it as a training facility. This gives us a unique opportunity to test research with the end user and get invaluable feedback. We see these 2 sites working as a phased approach. Pilot scale testing can be done in our own backyard at EFOB-L, and when projects pass key milestones, they can be moved to CBTEC and get hands-on comments from the soldiers. These test sites were key in the success of not only the hybrid power system, but multiple research efforts through our lab. Next slide. After laying the groundwork for our operational energy team, the question was asked, well, how efficient are we as the Army? If we want to be more efficient, we need a baseline. But no one knew because we had no data. So the first step in becoming more efficient was to gather that baseline. This drove the development of the Deployable Metering and Monitoring System, or DMMS. Next slide. The DMMS is a plug-and-play system that collects utility data and sends it wirelessly to a centralized database. You can kind of see in the slide here how we went through prototype improved to current, where we are now, which uses old power distribution boxes, and we insert all of our metering technology in there, leaving the intelligence in the box, which requires no new training for soldiers or end users. We also have engineering solutions, as we call it, which are externally installed, but provide the same capabilities. Using the custom open source dashboard at the centralized database, the warfighter can see data real time and make utility informed decisions to make their camp more efficient. Next slide. Using the DMMS, we can meter and monitor any relevant data. This data is stored and analyzed by our team. Next slide. Through the DMMS, we gained some international partners who wanted the same thing as we did. They wanted to collect data with an end goal of becoming more efficient. We worked with the United Nations to develop a DMMS system and installed it at one of their logistics bases in Bangui, Central African Republic. Using this system, the United Nations was able to change their power plan at that site and purchase more energy efficient generators to save them money. Next slide. We also work with NATO to develop metering standards that will be used across all NATO partners. We are co-directing a project with Canada. Canada is the lead. It's a Science for Peace and Security project, and this is key in developing those standards. Next slide. So how does this relate to the hybrid power system? Well, through all this data collection and analysis, we realized we're using our tactical generators at an average of 30% of their capacity. At this rate, generators are very unhappy. They wet stack, which sends unburnt fuel into the exhaust system and essentially kills generators way before their expected life cycle. We thought, wow, the Army really sucks at power generation. We're only using 30% of our capacity. Well, it turns out we aren't alone. As we broadened our vision, we saw that it wasn't just the Army, it was all services. And then as we looked even farther through our international partners and the data that they were gathering, we realized this is a worldwide problem. Everyone oversizes their generators to capture their peak load requirements, even if they're only running at 30% during their normal operations. Next slide. This drove our development of what we called the hybrid power trailer. It was our first prototype in the hybrid world, and the hybrid power trailer had power generation, power management, and energy storage on a 5-ton towable platform. It works like this. The load is connected through the hybrid power trailer, just like it would be from a generator. When powered on, the hybrid power trailer fires up the 15 kilowatt generator that it has on board, runs it at 90% capacity, no matter what the required load is. The power is sent to the load first, and any remaining power is sent into energy storage. For this system and most of our systems, we use lithium-ion batteries. We have 10 and 20 kilowatt hour packs, and on the hybrid power trailer, we had 40 kilowatt hours of lithium-ion batteries for energy storage. Once this energy storage is full, the generator shuts off, powering the load completely from batteries. When the batteries get down to a user configurable level, we normally try to keep it at 10 to 15% of battery capacity. The generator turns back on, runs back up to 90% capacity, and repeats the cycle. After getting user feedback from this system, mainly from the Marine Corps, we realized that not everyone has a 5-ton vehicle readily available. So we developed the Hybrid Power Trailer Light, or HPT-L. This is a Humvee towable system and essentially just removes the generator from the platform. It's designed to work exactly like the Hybrid Power Trailer, except it's pulled next to a generator and provides the same benefits. We also added the ability to connect multiple size generators. So for the Hybrid Power Trailer, we had the 15 kilowatt that was attached. For the Hybrid Power Trailer Light, we were able to use 15, 30, and 60 kilowatt generators, which are currently program of record. And we also added solar input. Next slide. During our pilot scale testing at EFOB-L of the Hybrid Power Trailer, we ran completely off tactical generators to power our site. Doing this, we averaged about 64 gallons of fuel a day. After powering EFOB-L with the Hybrid Power Trailer, we dropped that average to 11 gallons of fuel a day. You can see here a snapshot of how the Hybrid Power Trailer works from some of the data we took. The orange sections show when the generator is online. You can see it running. Again, it's a 15 kilowatt generator. You can see it running almost to 15 kilowatts and charging the batteries. Then the purple is when the generator is off and we're discharging solely from batteries. Next slide. The next step in our hybrid research brought us to make a more all-encompassing system. You can see in this diagram that we developed where we wanted to go. We wanted to pull power from host nations or non-programmer record generators first because, well, that's free power. And then we wanted to use solar panels to bring in power because, again, that's cheap. So we added an input for the Marine Corps Greens PV panel, which is a programmer record. Then finally, we would pull power from our own programmer record generators, which at this time is the amps. The system would work the same as the Hybrid Power Trailer and Hybrid Power Trailer Light, sending power to the load and anything left over going to the energy storage. We wanted to make sure to prioritize power. And as you can see in there, we have filters to clean up host nation or any other power that we bring in. Next slide. So this research drove the development of our hybrid power system, as we call it. And you can see our prototype in the pictures there. Using the lessons learned from the Hybrid Power Trailer and the Hybrid Power Trailer Light, we ruggedized most of the internal components. We now use racing automotive inverters that are liquid cooled, and most of our controls are moving over to automotive components as well. As the auto industry increases their technology, we increase ours. Again, the functionality of the HP hybrid power system is exactly like the hybrid power trailer. We've just added a lot more capability and a lot more ruggedization. We currently have a hybrid power system designated to support the 130th Engineer Brigade, which we sent over there, which is in Hawaii, and we transported over on a U.S. Army boat. And we've also transported these systems using mil-air. This is a very significant step because, as you know, transporting lithium-ion batteries as you go on an airplane or anything else is very frowned upon. So it was a very big win for us to get lithium-ion transported using mil-air. Next slide. So here's an example that C5ISR used. They're an Army Futures Command member, and they use our hybrid power system to develop one of their microgrid controllers. And one of the big things here is that the DoD is using the Tactical Microgrid Standard, or TMS, moving forward, which is driving the industry to make compliant systems. This proved that not only is the hybrid power system TMS compliant, it also can work next to multiple amps in a current microgrid setup. Next slide. So this is the way forward for the hybrid power systems. We're designing this system in particular to support AFRICOM's area of responsibility. As you can see, we changed the footprint significantly. We went from using a trailer mounted system to a footprint that matches the 60 kilowatt amps generator. And we did this for a couple of reasons. First, one of the big issues we had with the hybrid power system in its original footprint was thermal management. When running at full capacity or full 60 kilowatts, the hybrid power system and all of its internal components gets very, very warm. So this allows better cross breeze and gives us more control over the thermal management. This system also gives familiarity to the end user since it is in that 60 kilowatt amps generator footprint. It helps when moving it around and helps with transportability. The new HPS provides a separate platform for energy storage, which adds up to 106 kilowatt hours of lithium ion battery storage, as opposed to the 40 kilowatt hours we were getting before. Next slide. So the next thing we're looking at as we move forward is how to add more user-friendly energy storage options. The 6T battery format is already readily available through the supply system because it is the battery used on most military trucks. So adding this energy storage solution gives more flexibility, more reliability, because if we have battery failure downrange, we can just order a new 6T battery and replace the bad one. Next slide. Now I wanted to touch a little bit on a few other research efforts we're working on that will help develop and support the hybrid power system. We're developing a battery maintenance facility that will give us the capability to further research on energy storage. One of the big pushes with this effort is to make lithium ion more safe and more transportable. We have a few companies that we're working with that have developed new chemistries for lithium ion. We're also looking at how to bring lithium ion technology to the 6T battery format to further increase energy storage in that 6T format. Next slide. Another research effort we have is to revamp current lead-acid battery technologies. The objective of this project is to develop new technologies that extends the life of lead-acid batteries and provides a warfighter with an energy storage solution capable of providing both 30 kilowatt hours and also 250 kilowatt hours using lead-acid batteries. This project will develop 3 prototype energy storage systems with the ability to assimilate, manage, and monitor lead-acid batteries found across the operational environment. It will also develop a more ruggedized, open source, multi-use inverter to support mobile power sources, incorporate battery life extending cooling and charging methods, and tactical charging into the microgrid. Next slide. So we are also looking at flywheel technology for energy storage as an alternative to lithium ion or lead acid batteries. The objective of this effort is to evaluate composite flywheels for their capability to safely and adequately facilitate peak shaving, be used as an energy storage mechanism for a tactical microgrid, provide rapid charge and rapid discharge of stored energy, and reduce fuel consumption for deployed power requirements. So we're looking at developing a 216 megajoule, which is 60 kilowatt hour flywheel for compatibility with the AMPS microgrid. Next slide. Finally, we realized that Army is developing more high power weapons and high power radar systems going forward. Knowing that the current power plan will not be able to handle these new power requirements efficiently, we've been researching a way to scale up the concepts we developed through the hybrid power trailer and hybrid power systems. This hybrid electric large-scale power system, or HELPS, essentially puts a generator, power electronics, controls, and energy storage on a flat rack to sit next to these new technologies and provide the needed power more efficiently. Next slide. With that, I'll open it up to questions.
Thank you, John. Once again, if anybody has any questions, feel free to put them in down here in the questions pane of your chat. We'll be taking all of our questions from there. So one question that I wanted to start with here for you, John, is about why isn't there a commercial off-the-shelf system for this?
Yeah, so there are stationary systems available, but MIL standards are hard to comply with. There's the ruggedization that's needed for moving a system like this throughout the battlefield is something that hasn't really been looked at. And there was really no need until recently for anybody to develop something like this, because in the past it was, if you needed power, throw a generator down. Well, now that we're looking at how to do things more efficiently, this is the only solution that really makes sense.
Okay, all right. So here's a question from Drew Raw here. He asks, does the output deliver a conditioned supply, for example, like a hybrid UPS? And if so, what parameters does it deliver?
So I'm sorry, can you repeat that, the EPS?
Sure. Does the output deliver a conditioned supply, for example, like a hybrid UPS? And if so, what parameters does it deliver?
So it delivers, we can basically select the voltage that it comes out at. Right now, we're at 208 or 480 volts AC. And we can also choose if we want it to be 50 or 60 hertz. I think that answers the question, possibly. I don't, maybe.
Sure. Drew, yeah, if you have a follow-up question, Drew, feel free to put it in the questions here as well. Or if that answers your question, just let us know. And here's another question here from Norm Campbell, who asked, when is this system expected to be available for deployment to the troops?
So, as I said before, we have one system that we have sent to the 130th Engineer Brigade, and right now we're developing another system to send to AFRICOM. So I think we're there. We're right at the edge of being able to make this readily available for the troops. I think we've kind of gone through most of the hiccups and things like that from the research side. So yeah, if you want one, let us know. We can probably build one for you.
All right, thanks. And I believe Norm, we had talked earlier. I believe Norm is helping on some of the construction and building sides of this as well, if I remember correctly. So that's good to know. Thanks, John. I think we got one last question in here for you. Oh, we just had another question come in. So two more questions. Let me get this one first. So let's go back to you're talking about lithium ion. So why doesn't the military use lithium ion across the board instead of lead acid?
So lithium ion in general is a little more dangerous than lead acid. So if it gets, there's something called thermal runaway where it essentially just burns and it's very hard to stop. And also the transportation side, it's not as, you can just throw a lead acid battery anywhere and take it wherever you want. For lithium ion, it's a little different. As I said, we were able to send ours over to Hawaii, but we had to make sure we were at 30% state of charge, and there's other things that make it a little more difficult on the transportation side. So that's one of the research efforts we're doing going forward, is figuring out how to make it safer, because you can have the best technology in the world, but it doesn't do very good if you can't get it where it needs to be to help people. So those are the two big pieces why we haven't switched completely to lithium ion yet, but I think we're getting to that point as we go forward.
Mm-hmm. Yeah, no, it sounds like you're definitely working towards that, and so good to see some strides being made there with your research there. So we've got a couple more questions that have come in. So yeah, like I said, if you've got questions, feel free to pop them in the questions pane here. So this is a question from, and I'm sorry if I mispronounce your last name, Jackie Hoon, who asks, she sees an RFI stating 500 kilowatts, but your presentation shows 400 kilowatts. What is the U.S. Army looking for?
So I'm assuming she's talking about the hybrid, or talking about the hybrid electric large-scale power systems. So when we develop, or looking at developing that system, right now the current power plan for the Army is medium tactical generators, and that goes up to 60 kilowatts. They can be set in a microgrid, which can give up to 360 kilowatts, but that takes a lot of space to transport all those generators. So from that 60 kilowatt to the next step is 840 kilowatt, and that's a prime power, that's high voltage, that brings in a lot more needed support to install a system like that. So in the past, the Army had 100 kilowatt and 200 kilowatt generators. Those are considered legacy systems now, and they're not producing or supporting them anymore. So that leaves a big gap between that 60 and 840 kilowatts. So we just picked 200 to 400 because we know the requirements of, for example, the LTAMDS is a long-range missile defense system, and they're thinking that they're going to be coming in at a 200 kilowatt power requirement. So we're at the very early stages of development for this HELPS program. So we've kind of left the range open because as we move forward, we don't want to limit ourselves. If we need to go bigger or smaller, we have that option.
All right. Fantastic. Thanks, John. And then one last question here, again from Drew Brawl, about how reliable is the output? For example, does it deliver a reliable supply, and how consistent is it? For example, plus or minus 2.5% of nominal voltage and frequency. So if you could just speak to that, if you're able to.
Sure, yeah. So we've had it tested at Naval Surface Warfare Center, Carderock. They do a lot of power system testing. And we had, try to think of the number, I think it was 2 or 2.5 seconds from transfer between battery and power and generator power to get back on, to get the voltage back where it needed to be. So it's very quick, and you don't see, for example, if you're powering a fan or a heat, something like that, or a pump, and as it switches from one to the other, you don't see or hear any noticeable drops in voltage or anything like that. Yeah, so very reliable, very quick to recover a voltage as it changes, and yeah, hope that answers it.
Okay, so thanks, John. I think that that is about it. I want to thank you again for coming on out and presenting here today, and thank you to everybody who attended today's webinar. If anybody is interested in submitting an article for the military engineer, please feel free to visit our website for our editorial calendar and the guidelines. We actually are available, we're open for submissions for our upcoming March-April 2021 issue right now, which will focus on energy again. If you have a topic that you think would be interesting to your fellow engineers, that you'd like to get some visibility on, feel free to send them our way. I'd love to take a look at them. Make sure to download the PDH certificate and the handouts with a slide deck from the handouts tab before you leave today. There's a lot of good information in there from John for you to dig into. After leaving the webinar, you'll be directed to a brief survey on the presentation. Please fill it out if you can. We greatly appreciate any and all feedback that you can give. So on behalf of SAME, the military engineer, and our featured presenters, thank you for joining us today, and have a great rest of your day. Thank you again.